Hello friends, welcome to the today's lecture. Please recall that in previous lecture we have discussed the solution method for this kind of Fredholm integral equation of y of x equal to f of x plus lambda a to b k of x of t y of t dt, and we have seen that this solution can be written as y of x equal to f of x plus a to b lambda gamma x of t lambda f of t dt, and where gamma x t lambda is given as d of x t lambda divided by d lambda. So it means that the solution of the given Fredholm integral equation can be given by y of x, where gamma x t lambda is a resolvent kernel given by this ratio of two infinite series. But the problem arises when this lambda is coming out to be the root of d lambda, or you can say that this solution is valid when d of lambda is not equal to 0 for this lambda. But when d lambda is equal to 0, then how we can define our solution? Then please recall, then our d, once we know the d lambda, then your d of x t lambda is defined as by this following relation, that k of x t d of lambda plus a to b k of x of s d of x s of t lambda s t lambda dt. Here we know that once we have expression for d lambda, that is Fredholm determinant, then we have calculated the Fredholm minor, that is dxt lambda, with the help of this integral equation. This is a relation held by d of x t lambda. So and then we have seen that if d of lambda, this we have already done, that if d lambda is given by c naught plus summation minus lambda to power m upon factorial m cm, m is from 1 to infinity, then with the help of this integral equation we try to find out. We have already discussed that d of x t lambda you can calculate c naught of x of t plus summation m is equal to 1 to infinity minus lambda to power m upon factorial m cm x of t. So it means that this, with the help of this equation and the expression for d lambda, we have calculated the expression for dxt lambda, and also we have seen that if the kernel k is integrable and bounded, then expression given as d lambda is a uniform series for in terms of lambda for all values of lambda. Similarly, you can say that in the condition that this kernel is integrable and bounded, then dxt lambda is also this infinite series is also uniformly convergent for all values of lambda here. So this we have already discussed. Now the case with the help of this integral equation only, we try to consider the case when d lambda is equal to 0. It means that, let us say that you have the value lambda equal to lambda naught such that d lambda naught is equal to 0. So it means that here we are taking the value lambda naught. So here for this particular value your d lambda naught is simply 0. I am just considering the value lambda equal to lambda naught. So this part is simply vanish. So you can write it d of x t lambda naught is equal to lambda naught a to b k of x of s d of s t lambda naught d of t. Is it okay? Now I am saying that first we will consider the case when f of x is equal to 0, means that we are considering the homogeneous part. So here we are considering that when d lambda is equal to 0 and we are assuming that f of x is equal to 0. So it means that we are considering only the homogeneous part. Then we say that in this case your equation is this: y of x equal to lambda a to b k of x of t y of t dt, right. Okay, so this small correction here, this is correction is this, that here this integral is with respect to s, not with respect to t. So here integration is with respect to d of s. So here it is d of s. Okay, so here if we compare the equation and this equation, so if we compare these two equation, you can see that here if I assume that dxt lambda naught is non-zero, identically not equal to 0, then I can assume that y of x is equal to d of xt lambda naught is a solution of this particular equation for every value of t in the interval a to b. So it means that this y of x equal to d of xt lambda naught is a solution of this equation for all t in this interval a to b. Is that okay? So only thing we are worried is that this expression whether it is 0 or not. So this part, this discussion we can write it in this particular part, that if d lambda naught is equal to 0, so here we are assuming that lambda naught is a root of this Fredholm determinant, that is d lambda naught equal to 0, and we also assuming that dxt lambda naught is not equal to 0 or not identically equal to 0, then we can choose any value of this t and we can say that y of x as d of x t naught lambda naught is a solution of this equation, that is y of x equal to lambda naught a to b kxt yt dt. So that is clear from this. So here if you compare these two equation, this, and we can say that y of x equal to dxt lambda, which is not identically equal to 0, is a solution of this equation. Now the thing is that the condition that dxt lambda naught is not equal to 0, how we can rectify this. So here this condition that dxt lambda naught is not identically equal to 0 can be related to the expression Fredholm determinant d lambda in this way, that if you look at the expression for d lambda and if we differentiate that, then we have this relation. So just let me see what is this relation. So here we have this d lambda, that is small c naught plus summation m equal to 1 to infinity minus lambda to power m small cm upon factorial m. So if we differentiate this d dash lambda, you will get minus m equal to 1 to infinity, this part is simply vanished. So minus you will get minus m minus lambda to power m minus 1 upon factorial m and cm, and if you simplify this you will get this as minus summation m equal to 1 to infinity, this is m, it will cancel out here, minus lambda to power m minus 1 upon factorial m minus 1 small cm, and we know that small cm is connected with capital Cm minus 1 x comma x dx like this. So using this I can write it minus summation m equal to 1 to infinity minus lambda to power m minus 1 and upon factorial m minus 1, this Cm I can write it as integral of Cm minus 1 x comma x d of x, and if we simplify if you replace this dummy variable m minus 1 by say some n new, you can write it here that it is minus n equal to 0 to infinity minus lambda to power n upon factorial n and integral here Cn x comma x d of x. Now this infinite series is uniformly convergent, so we can interchange this integral sign and you can write minus integral of, and if you take inside it is nothing but your d of x comma x lambda d of x. So it means that your d dash lambda is related to d xx lambda in as this equation number 48. So it means that if we have lambda naught in a way such that d lambda naught is 0, but d dash lambda naught is non-zero, or we can say that lambda naught is a simple 0 of d lambda, then this portion d dash lambda naught is non-zero. So you can say that integral of dxx lambda naught dx is not equal to 0. So it means that this expression dxx lambda is not ideally equal to 0. So we can say that when lambda naught is a simple 0 of d lambda, then this y of x equal to dx t naught lambda naught is a solution of the homogeneous Fredholm integral equation of this y of x equal to lambda naught kxt yt dt. So in this case not only dxt lambda but any constant multiple of dxt lambda will be a solution of the homogeneous equation, this equation. And now we try to consider, we generalize the case here. So here we have discussed the case when lambda naught is a simple 0 of d lambda. Now what happen when lambda naught is 0 of d lambda with multiplicity say uk. So it means that d lambda naught is 0 and up to dk minus 1 lambda naught is equal to 0, but the kth derivative evaluated at lambda naught it is not equal to 0. So here we say that that lambda equal to lambda naught is a 0 of d lambda of the order k, right, and here we try to find out the solution of our homogeneous Fredholm equation given by 47. So let me summarize here. When lambda naught is simple 0, then dx t naught lambda naught is going to be a solution of this. Now we want to show that if lambda naught is a 0 of d lambda with multiplicity k, then in that case what should be the extended or what should be the generalization of dx t naught lambda naught. So here for this we define a new term which is known as nth Fredholm minor, and it is defined as dx1 x2 xn t1 t2 tn with respect to the given constant lambda, and it is given by k x1 t1 x2 t2 to xn tn plus p equal to 1 to infinity minus lambda to power p factorial p. This is a p integral k x1 to xn t1 to tn u1 to up u1 to up du1 du2 dup. So if we can define nth Fredholm minor as defined as 49, then our claim is that this will be a kind of solution candidate for the homogeneous integral equation. Now if you look at your equation number 49 in a clear manner, if we take n equal to 1, so it means that we are considering the first Fredholm minor. So our claim is that this is nothing but your dxy lambda. If you look at equation number 49 and write down the expression for n equal to 1. So here if you look at this expression d of say x1 to xn and t1 to tn with respect to lambda, which is given as k x1 to say xn t1 to tn plus summation your p equal to 1 to infinity minus lambda to power p upon factorial p, and this is p4 integral, and here we have k x1 to xn t1 to tn and then u1 to up and u1 to up and du1 to dup. I hope we already know this symbol, right? So using this symbol we can say that your dxy written like this. So now here if we take n equal to 1, then we try to see that this is reduced to your Fredholm minor, that is dxy lambda. So if you look at n equal to 1, then it is what dx1 t1 given as lambda is equal to k x1 t1. Now if you look at the notation here, this is what this is notation is determinant here x1. So this is, we already know that it is k x1 t1, k x1 t2 and so on, k x1 tn and so on. So here it is k xn t1 and k xn tn. So here using this notation you can say that k x1 t1 is nothing but k x t1. So let me write it first and then we will simplify this. T1 plus summation p equal to 1 to infinity minus lambda to power p upon factorial p, and this is p integral and this is k x1 and this is t1 and then u1 to up and u1 to up and du1 to d of up. So if you simplify, this is what this I can write it as, let me write it this as x1 t1 and lambda. This is what k x1 t1 using this notation, it is nothing but 1 cross 1, that is k x1 t1 plus summation p equal to 1 to infinity minus lambda to power p upon factorial p. And if you simplify this, you can say that this is nothing but Cp of x1 t1. So and this I can write it as C naught x1 comma t1. So it means that this is the nth Fredholm minor is a generalization of this Fredholm minor for n equal to 1. So I can say that if we want to write it, this is equal to this. Okay. So it means that this is the nth minor is the generalization of Fredholm minor, or you can further simplify this as follows. If you want to write it, you can write this as d p x say y lambda, or this is written as d of p is 1, p is n here, let me write it here. So I can say that this is d n x y lambda, it is d x1 to xn, t1 to tn lambda. Let me write it here, this I can write it here as b naught x say b naught x y plus summation p equal to 1 to infinity, you can write it bp this xy, okay, x y, right. So here b naught xy is defined as what, b naught xy is given by this thing. So here you can say that x is nothing but your x1 to xn and y is your t1 to tn, and b naught xy is defined as this. So this you can call it b naught xy and this you can call it your bp of xy. So if you define it like this, then this is nothing but generalization of the first Fredholm minor. Okay. So we try to show that in this is going to give you the solution of the homogeneous Fredholm equation. So here let us relate this nth Fredholm minor with the derivative of Fredholm determinant, that is d lambda. So if we look at, we have already this kind of relation given as 48. So when n equal to 1, we have a relation that d dash lambda is equal to minus dx comma x lambda. Now in the case when n is more than 1, then do we have any relation of this 48 kind? Then here we will not do it, but when you differentiate d of lambda, that is Fredholm determinant, with nth times, you will see that it is coming out to be minus 1 to power n. This is n times n fold integral d of x1 to xn, x1 to xn lambda dx1 to dxn. So it means that we do have the similar kind of relation as we have seen that d dash lambda equal to minus integral of dx comma x lambda. Similarly, this equation number 55 shows that when n is more than 1, then also we have a similar kind of relation, and we say that if lambda naught is a 0 of multiplicity k of the function d lambda, then means what, that dk lambda naught is non-zero. So it means that with the help of this equation number 50, we can say that the kth minor of kth Fredholm minor, that is dx1 to xk, x1 to xk, t1 to tk given this lambda naught is not equal to 0. So it means that if this is a kind of a relation between the zeros of d lambda and the solution candidate, that is this. So it means that if lambda naught is a 0 of multiplicity k of this function d lambda, then kth minor is not equal to 0, but we may have that there is a k minus 1th minor or say k minus 2th minor may also not be equal to 0. So it means that we can always choose a number q which is less than k, such that the qth minor of Fredholm kth minor of d lambda is not equal to 0. Okay, so with the help of that we can define the notion that is index. Okay, so we will define it later on, but before that we try to see that this nth minor, nth Fredholm minor will satisfy a similar kind of integral equation. So if we know that this dxy lambda is equal to k of x t d lambda, I think I have to write t here, that dxt lambda is equal to kxt plus d lambda plus lambda a to b k k of x of s d of s t lambda d of s. So it means that we already know that this Fredholm minor satisfy this relation. We want to know that the generalization, that is nth minor of nth Fredholm minor, will also satisfy similar kind of equation or not. So for that what we try to do here, we look at the similar kind of expression. So here if you have this expression nth minor of the nth Fredholm minor of d lambda, and if we expand this determinant with the help of say along the alpha row, and when we simplify we can get this kind of relation 52. This simplification involves a lot of say calculation thing, so I am not presenting here the calculation part. The only thing I am giving here is that this this nth minor of d lambda will satisfy this integral equation 52, and this when you are doing the expansion of your determinant along the alpha row. If you do the same expansion along the beta column, then we also have this similar kind of integral equation. So here if you look at this equation number 52 and the equation number 53 is kind of integral equation similar to the integral equation satisfied by dxt lambda. So we try to see that this equation number 52 and 53 will give you say some method to find out the solution when your d lambda is not equal to d lambda is equal to 0. So here as we know that this expression then dxt lambda is a basically you can find out this expression is valid for all values of lambda. In the same way you can say that your 52 and 53, these two expression is also hold for all values of lambda. So not only those values for which d lambda naught is equal to 0, it valid for all values of lambda. So with the help of this 52 and 53 we try to now discuss the case when d lambda naught is a 0 of d lambda. So now we can say that this 52 and 53 we try to get this, that we can find the solution of the homogeneous equation for the special case when lambda equal to lambda naught is an eigenvalue. So let us assume that this lambda equal to lambda naught is a 0 of multiplicity k of the function d lambda. So it means that d lambda d dash lambda up to d to power k minus 1 lambda naught is equal to 0. Let me write it here so that, so here we know that lambda equal to lambda naught is a 0 of multiplicity k. So it means that d lambda naught is equal to 0 and equal to d dash lambda naught is equal to 0 and so on up to dk minus 1 lambda naught is equal to 0, and your dk lambda naught is not equal to 0. Okay. Now we know that from this relation, that is minus 1 to power k dk lambda naught is equal to your relation, if you remember equation number 50 here, this relation that dk d and d lambda differentiation of d lambda with respect to lambda n at time this 50. So it means that if dk lambda is non-zero, so the corresponding kth minor is also non-zero, right. So it means that this implies that the kth minor of d lambda is also not equal to 0, but it may happen that this k minus 1th minor or say anything lesser than that is also equal to also not equal to 0. So what we try to do here, we try to find out say the value of r for which just a minute here here. So here we already know that lambda equal to lambda naught is a 0 of multiplicity k of the function d lambda, then the minor dk does not identically vanish, even the minus d1 to dk minus may not identically vanish. So let us find out say r says that dr be the first minor in the sequence d1 to dk minus 1 that does not identically vanish. So it means that before that it means that dr minus 1 is equal to 0. So that means that that k minor is not vanishing. It may happen that this k minus 1th member minor will also not vanish. So what we can choose say r which is between 1 to say this k such that rth minor of d lambda does not vanish, but r minus 1th minor of d lambda is equal to 0. Is that okay? So it means that if we do this, we such a number, this r, such a number is called index of lambda naught. So if r is the index of lambda naught, that is rth minor of d lambda does not vanish, but r minus 1th minor of d lambda is equal to 0. In fact any minor whose order is less than r of is going to vanish. In that case equation number 52 reduces to this integral equation, that is dx1 to xr t1 to tr lambda equal to integral k x alpha u dx1 to x alpha minus 1. Please remember that this k x alpha u means at alpha position there is a u. So x alpha position here is replaced by this u and du u. So if we already know that r is the index of the number lambda naught, then this expression is not going to be, so rth minor is not going to vanish. So it means that this is a non-zero quantity. So if it means that this dx1 to xr t1 to tr, this rth minor satisfy the homogeneous Fredholm integral equation. So here we can say that if we substitute x at different points of the upper sequence in the minor dr, we can get our non-trivial solution yjx, which is defined like this. So here what we are doing here, we are replacing the ith upper position, ith position of upper sequence by x and divided by d of r here, and we can say that this phi of x, which is so this ratio is the function of x, and we can say that this phi of x is the solution of the Fredholm integral equation, which is homogeneous here. So here in this way we can get r number of linearly independent solution of this. Please look at here the expression given in terms of 55. Then here if I represent phi of x by that expression, then if I look at fi of x alpha, right. So it means that at alpha position, if we take the x alpha, so it means that if I take here, if we take phi I x alpha, means at ith position if we take x of alpha, then this numerator is going to vanish, because that represent that your ith row is identical to the alphath row here. So it means that if we take x as x alpha and alpha is not equal to I, then in that case numerator is going to vanish, because of there in this determinant there are two rows which are identical to each other. But if I take the x as xi, it means here if we take x as xi, it means that phi I xi is then this expression is same as the expression given in denominator. So it means that in this case when x is replaced by xi, then phi I xi is nothing but your 1. So I can say that phi I x alpha is equal to 0 if alpha not equal to I, and it is equal to 1 when alpha is equal to I. So this means that these phi I x given by this is having this particular property, that phi I x alpha is equal to 0 when alpha not equal to I, and equal to 1 when alpha equal to I. And with the help of this property you can easily check that the solution phi I x for I is equal to 1 to say r, these are linearly independent solution. In fact you can easily check that summation Ci phi I x is equal to 0, I equal to 1 to r, and then you can replace x equal to say xj, and you can check that all the corresponding coefficients ck's are equal to 0. So in this way we can say that all the solution given by this phi I x are linearly independent. Please remember that r is the index of d lambda corresponding to lambda equal to lambda naught. So here now we can summarize the discussion in the theorem which is known as Fredholm's second theorem. It says that if lambda naught is a 0 of multiplicity n of the function d lambda, then the homogeneous equation yx equal to lambda naught kxt yt dt possesses at least one and at most n linearly independent solution in terms of which every other solution is expressible linearly and homogeneously, and this system of n independent solution is given by the expression here phi alpha x equal to d x1 to x alpha minus 1, at alpha position it is x alpha 1 to xn, and in this t1 to t beta minus 1 t beta and tm, and in denominator it is the nth Fredholm minor of d lambda. Is it okay? And then let us consider one example based on this Fredholm's second theorem. So here example is y of x equal to lambda 0 to 1 minus 3 xt yt dt. If you remember we have already discussed this example with the help of Fredholm's first theorem. So here we are considering the homogeneous equation. Now as we have done in previous lecture, we can calculate all these CIs, and you can see that your d lambda is given by m equal to 0 to infinity minus lambda to power m factorial m small cm, and all these CIs are already calculated in previous lecture. Similarly we can write it here, and you can say that d lambda is nothing but 1 minus lambda square by 4, and if you look at d lambda is equal to 1 minus lambda square by 4. So if I take lambda in a way such that d lambda is equal to 0. So let us take lambda equal to plus 2 or minus 2. So we can say that this lambda equal to plus minus 2 is known as the eigenvalues of the equation, integral equation, and in this case your dxt lambda, which we have already calculated, let me write it here, dxt lambda is given as 1 minus 3 xt plus minus lambda times minus 3 xt plus 3 by 2 x plus t minus 1, and when you simplify this is for lambda equal to 1, lambda equal to 2, dx t2 is given as 3 of 1 minus x 1 minus t. So it means that here your d of 2 is equal to 0, but d dash lambda is not equal to 0 at lambda equal to 2, that you can easily verify here. Then in this case we have already seen that in this case your solution y of x is given as d of x say some particular value of t, so let us say t naught and 2. So that is going to be a solution of this. So here we just try to see that for lambda equal to 2, dxt lambda is reduced to 3 1 minus x 1 minus t here, and for lambda equal to 2 minus 2, you can say that dxt lambda is given by 1 minus 3x into 3t minus 1. So we can say that in this case, if we apply the result, which is Fredholm's second theorem, that if lambda naught is a 0 of multiplicity n, so here n is equal to 1, in that case we have at least 1 and at most 1. So we can say that at least one solution is given, and that solution you can find out by nth minor of your Fredholm of d lambda. So here first minor of d lambda is given by dx t lambda. Okay, so here we can say that corresponding to lambda equal to 2, the solution y of x is given by d of x t lambda. So here lambda is equal to 2, and you can take any value of t. So when you put lambda equal to 2, it is reduced to 3 into 1 minus x 1 minus 2. So it means our claim is that for any value of t, this expression 3 into 1 minus x 1 minus t is a solution of the homogeneous integral equation. So that we can verify here. So we can take, let us say t equal to s, you can take any value of t here. So let t equal to s, and we can verify then this expression dxt lambda is going to be a solution of this. If you calculate, it is coming out to be 1 minus s 1 minus x. So it means that this expression gives you a solution of your homogeneous integral equation for lambda equal to 2. Similarly you can do for lambda equal to minus 2. So you can check that for lambda equal to minus 2, this expression dxt lambda equal to 1 minus 3x 3t minus 1 is a solution of the homogeneous integral equation for any values of t between this 0 to 1. Okay. So let us try to find out the solution for non-homogeneous equation. So that is the content of Fredholm third theorem, which says that this inhomogeneous equation or non-homogeneous equation yx equal to fx plus lambda naught k a to b k x t y t dt will have a solution in the case when lambda naught is a 0 of is a root of d lambda naught of index n, and the necessary and sufficient condition for this is that the function f of x is orthogonal to all the eigenfunction phi j bar x of the transpose homogeneous equation. What is the transpose homogeneous equation? That your phi j bar x is the solution of this equation lambda naught a to b k t x phi j bar t dt. So if you remember the homogeneous part is lambda naught k x t y t dt. So it's the transpose equation is this lambda naught k t x phi j bar t dt. So if we can find out the solution of this transpose homogeneous equation with the help of Fredholm's second theorem, and fx is orthogonal to all those phi j bar x, then your solution is given by this y of x equal to f of x plus lambda naught, and if you remember we have this is nothing but phi j x here. So plus p equal to 1 to n cp phi p x. So here this we can denote as say some hx y lambda naught, this is kind of resolvent kernel in this particular case, and this phi p is the solution of the homogeneous integral equation. So so it means that in this case if fx satisfy this condition that it is orthogonal to this and phi j bar satisfy the associated transpose equation, then solution is given by this. And so this we can find out with the help of Fredholm's second theorem, which we have discussed earlier. So this is the simple generalization of Fredholm alternative theorem. So here we will stop, and so we can summarize it like this, that Fredholm first theorem is giving you the solution method when d lambda naught is not equal to 0, and second theorem gives you the solution of Fredholm integral equation which is homogeneous in the case when d lambda naught is equal to 0, or you can say that lambda naught is a root of d lambda of multiplicity say m. And in Fredholm third theorem we try to find out the solution of non-homogeneous integral equation. And thank you for listening us. We will meet in a next lecture. Thank you.